Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 33, and it is entitled Ideal Gas Laws. When we deal with ideal gas laws, there are several historical figures that come to mind, and you will not be asked these names on the AP exam, but it would be remiss of me as an instructor not to mention some of these folks. Let me write their names down, and we'll talk about them in turn in particular future moments in time. Here are some of the giants that have developed one or another idea dealing with ideal gases. Boyle, Charles, Gay-Lussac, Avogadro, Dalton, Boltzmann, Maxwell. These are important names. If you're going to be dealing with ideal gases, then it's important to know what an ideal gas is. So let's define what we mean by an ideal gas. It turns out that real gases, under conditions that we would consider to be ordinary, which means that they're not under very high pressures and they're not at very cold temperatures, will behave approximately as ideal gases, and that's the only kind of thing you're going to be asked about on the AP exam. So this is an approximation that we're willing to make. First of all, ideal gases are made of point particles. All of these particles are identical to each other, and there's not a mixture of one type of particle or another type of particle together in the same container. Now, it's possible that there are different types of gases that can be modeled, but we're not going to mix different gases. These point particles all have the same mass. We'll call that mass m. Another point is that these point particles are moving inside a closed container with a variety of random velocities. Some of the particles are moving slow, some of them are moving fast. They have some random distribution of velocities. These point particles don't interact with each other or interact with the walls of the container unless they actually physically bump into each other. What we mean by this is that there is no potential energy term that we're going to have to deal with when the gas particles are moving around. The only kind of energy that the particles will have will be kinetic energy. And whenever the gas particles collide with something, they're going to be completely elastic collisions. Whether they're with each other or whether they are with the walls of the container, all the collisions are completely elastic, which means that linear momentum is conserved and kinetic energy is conserved. All of these assumptions, this model, is put forth under a theory of matter that is called kinetic theory, that attempts to connect mechanical properties of the particles, like kinetic energy and the forces that are exerted on the particles during collisions, with temperature. And so this kinetic theory that we're developing here tells us that there is a relationship between the mechanical properties of the particles and the thermal properties of the gas. The mechanical properties are at the microscopic level, the thermal properties are at the macroscopic level. And when we have Avogadro's number of particles, 10 to the 23rd, it's hard for us to be able to talk about the motion of individual particles. So we tend to try to put those things under a group and deal with them all at once macroscopically in thermodynamic quantities. So this kinetic theory is going to try to talk about the momentum and the kinetic energy of this Avogadro numbers of particles with macroscopically measurable quantities such as pressure and volume and temperature. Those are the things that we're trying to connect together. I have a simulation that I would like to show you of a gas. In this simulation, I have a closed container over here that has a temperature thermometer here and a pressure gauge and has an ability for me to change what the volume of the gas is. I can open a container and let gas particles out if need be. I can add heat to the container, or I can remove heat from the container, and I can put different kinds of species of gas in. For right now, what I want to do is I just want to pump a few gas particles into this container, and let's look and see what's going on. So here are a few gas particles. Again, these are point particles. You can see they're moving around in random directions. Some of them are moving fast, some of them are moving slow. They're bouncing off the walls of the container, they're hitting each other, and now I'm going to freeze the motion here for just a moment. This has only a few gas particles in it. If I'm going to count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I got about 25 particles in there. And we can see that if I were going to try to follow all 25 of those particles, I would have a hard time doing it. That's just 25 particles. Let me add some more particles. All right? These particles are nowhere near Avogadro's number of particles. But whatever they are, I can, at some moment in time, take a snapshot of those particles and talk about how fast, on average, that they're moving. And in particular, talk about their average kinetic energy. And it's this average kinetic energy that we're interested in when we talk about the temperature, the absolute temperature of the gas. So let's go back and discuss a little bit more about kinetic theory. Kinetic theory tells us that there is a relationship between the temperature, the absolute temperature, and the average kinetic energy of the gas. We need to define a new quantity, and that new quantity is called the internal energy of the gas. And the symbol that's used for internal energy is the symbol capital U. The internal energy U is defined to be the sum of the kinetic energy of all the particles in this gas. So if I have 25 particles of the gas, then I would say that the internal energy is equal to the kinetic energy of particle 1, plus the kinetic energy of the particle 2, plus the kinetic energy of particle 3, plus the kinetic energy of particle 4, and I do that all the way up for all 25 particles. And in mathematics, the way we can show this sum is with a summation notation. If I have n particles of gas, n could be 25, then basically I say kinetic energy of particle 1 plus the kinetic energy of particle 2, all the way up to n. And if I wanted to, I could rewrite this in terms of 1/2 mv squared. Now, I'm not going to get very far into this because this is actually a topic of something called statistical mechanics. But what I want to show is that there is a connection between kinetic energy and temperature. And here is what that connection is. This equation, U, the internal energy, is equal to 3/2 times little n, the number of moles of gas, times R, something we'll call the ideal gas constant, times T, which is the absolute temperature of the gas. This equation comes from something that is called the equipartition theorem to figure out what the kinetic energy and temperature relationship is. On the left-hand side, there's the kinetic energy of the gases, particles, and on the right-hand side is the absolute temperature. Here's the meaning of the symbols. What this equation tells us is that the absolute temperature is a measure of the average kinetic energy of the gas particles. Here, this explicitly gives us what that connection is. We are not so much interested in the numerical value of the internal energy. We're more interested in what happens when internal energy changes. And it is this equation that involves changes in internal energy that we're mostly going to be primarily concerned with. If those of you who are in calculus wanted to do a differentiation du dt, then that's what we're going to do, but we're going to talk about it in terms of deltas. So let's talk about the change in internal energy that comes with changes in temperature. This orange equation, the one that says changes in internal energy are equal to 3/2 times n times r times delta t, is the equation that we're going to use more and more when we get to thermodynamics, the first law of thermodynamics. And we're going to see that these changes in internal energy in a heat engine, say like an automobile engine or in a steam turbine, are going to occur as a result of work that can be done on the gas or heat that can be transferred to the gas. And so we're going to be interested in relating those things together in future lessons. For right now, we're interested in writing the ideal gas law, and I'm just going to give you that gas law. This is something that you've seen in chemistry before, and it's this ideal gas law that's a combination of Boyle's law and Charles's law and Avogadro's law and the law of Gay-Lussac. It puts all of these things together. Here's what it says. PV equals nRT. P stands for pressure, V stands for volume. The little n is the number of moles of the gas, R is the ideal gas constant, and T is the absolute temperature. You will see this sometimes written in other texts in a different way, which I will write down here. PV equals capital N times KB times T. But on the AP exam, you are probably not going to have to deal with the ideal gas law in this second form. The first form is the form that chemists like. That's the way that you're going to see it on this AP exam. The second form is the physicist's way, and the difference between them has to do with the numbers of particles, capital N, versus the number of moles of gas, little m, and it has to do with the gas constant. Kb stands for Boltzmann constant, named after Ludwig Boltzmann that we talked about earlier. R is the ideal gas constant. We're not going to worry about that. We're going to deal with the red equation, PV equals nRT. Now, before we actually solve some numerical problems, I want to point out to you that when you deal with gas laws, the units that you deal with will sometimes be very important, and sometimes they will not be important. And how do you know when they are and when they're not? And hopefully that will become clear as we solve some problems. Sometimes you have to pay attention to what units there are, and there are going to be MKS units, and there are going to be many other units as well. Let me write down what some of them are. For instance, when we deal with pressures, you're going to be dealing with the MKS unit for pressure, which are pascals, newtons per meter squared. But you'll also deal with kilopascals, and atmospheres, and torrs, and millimeters of mercury, and pounds per square inch. When volumes are discussed, the MKS unit for volume is going to be a cubic meter. But you can also deal with cubic centimeters, or liters, or milliliters, or cubic decimeters, or cubic inches, or gallons. There could be all sorts of volume units. And temperatures. You'll sometimes see temperatures given in degrees Kelvin. That's the MKS unit, and every time you deal with ideal gas laws, you must convert to absolute temperature. There's no way around that. Whenever the ideal gas law is dealt with, absolute temperature has to be involved. But sometimes you'll be given temperatures in degrees Celsius, sometimes even degrees Fahrenheit. Probably not on the AP exam, but you'll encounter them in everyday life. So be aware that you've got all these different units. So how do I know when units are important and when they're not? Frequently, you'll find that you can get away with dealing with non-MKS units if there are ratios that are involved, and many of the units will cancel out. On the other hand, if you're asked to find something that deals with a specific energy, then you'll find that you may have to convert things to MKS units. And that's just going to be something that you have to practice, and practice makes perfect in terms of recognizing these things.